Thank you so much for that great introduction. Hello, everyone. My name is Sarath Sreedharan, and the topic we'll be talking about is going to be synthesizing explainable and deceptive behavior for human AI interaction. So, unfortunately, due to the corona crisis, I'm stuck in this small room, and it's kind of early for me in Arizona. So I apologize if I look a bit sleepy. But again, so as was being mentioned, so this is going to be kind of a modified version of an earlier tutorial that was given in IEEE 20. So before we start, I wanted to give a huge shout out to the other co-presenters in that earlier tutorial, from whom a lot of these materials has been taken and kind of adapted for this specific one. Okay, so let's just get started. I hope all of you would agree that we are living through really exciting times for AI. So we see AI application in a lot of different domains, and every day you see in news about the new incredible things AI systems are capable of. So here are just some screenshots from some impressive AI application. So you have rovers in other planets, you have medical robots, you have, in fact, there are automated cars in the roads of Phoenix where I stay. So there are all of these exciting developments happening in AI, but unfortunately we are still far from having really robust, complex AI systems that we can work with in everyday life. So one of the things that if you had kind of followed these applications, these specific applications I kind of pointed out, they usually require someone with expertise to use these AI systems. So what is really missing is at this point, it's very hard for a everyday user to just start using a complex AI system and expect the AI system to behave in ways that make sense to the person who it is interacting with. And one of the reason why we don't have these kind of fluent teaming and interaction between humans and robots, one of the key missing pieces is, I would say, is explainable systems, as in systems that are capable of either acting in ways that make sense to people or are capable of giving explanations in intuitive terms when it cannot do so. So the focus of this tutorial is how do we generate AI systems that are capable of doing this? And the answer I will go put forward, and hopefully you will all agree, is the fact that what's missing in most of today's AI systems is the capability to model the people. Most of the AI systems is focused on, in some sense, modeling about the task and reasoning about how to solve the task. And what's being missed is kind of reasoning about the people it will be interacting with, the mental models of these people, what their expectations are, beliefs are, and more importantly, what their expectations about the systems are. As in, like, what do they expect the AI system, how do they expect the AI system to behave? What are the beliefs they ascribe to these AI systems? And the hypothesis we put forward to it is that's modeling and capturing these information is central to creating successful explainable systems. So just to kind of give a little bit more motivation here. So this is just your standard intelligent agent architecture. Hopefully most people who are familiar with the textbook AI, a modern approach, would have seen some form of this architecture. So this is how I would say, at least as of right now, our standard view of what an AI agent should be, right? So you have a robot, in some sense an agent. I'm just using the word robot to kind of make sense, talk about just an AI agent. It doesn't have to be physically embodied, but they usually have some actuators in some sense that would it can use to manipulate the world in some sense. And it has some sensors that it uses to detect what the state of the world is. And it tries to reason about, given the current state of the world, what kind of actions it needs to do so as to achieve its objectives. And so this is kind of your traditional goal-directed agent architecture. This is where we are right now. And where we want to be is something like this. I'll go through the details of what this exactly is, but the kind of the big picture here is to kind of realize that it's not just enough for the AI system to model the world and how its actions would affect the world, but also kind of think about the people in the world, right? What their mental models are, what their beliefs are, and how the agent's action would influence those. And this has to be taken into account while coming up with its decisions. So that's the big picture here. Again, this is a part like this is there was a sister tutorial to what we are going to talk about, which was presented in IIII 2020, and you can also find a video link. That tutorial was much more broader in scope, so they covered a lot of topic. What I'm hoping to do here is like focus on some specific topic and dig a little more deeper, so you get a bit more clearer idea of some of these techniques and things. And we also have a book in preparation about these topics. So these are some resources you guys can go back after this tutorial to kind of get a more more information about the topics we'll cover here. Okay, so before we get into the nitty-gritty details of the specific task, I just wanted to say that most of the discussion we'll have today is going to be centered around planning. So I'm not sure that all of everyone's background here. So I just wanted to give like a very high level overview of what I mean by planning. For the sake of this tutorial, it's not really required to understand specific planning techniques, but it would be helpful to kind of at least have a common ground when what I mean when I say planning. So to start with, right, planning is a way of doing sequential decisions. So what is sequential decision making problems, right? Like going back to our architecture, like our agent architecture, here the goal of the agent is to come up with a sequence of actions so that it will achieve its objective. So it's not just enough for the agent to come up with one actions, but it has to think about how it can chain its action so as to achieve its objective. Maybe it's a goal. Maybe it's trying to optimize some objective and so on. So planning can be understood as a model-based method of doing sequential decision making. Generally, the goal here would be to use a planning model to come up with a plan of action, a policy, or in some way generate a behavior that it will be executing in the world. So the question you might have is, what do I mean by planning model? In a sense, like at a high level, you can understand planning models as being a representation of the task at hand that the agent is trying to solve. And what that means is it's in some sense capturing the dynamics of the world, in the sense that it's capturing how the agent's action would affect the state of the world, right? What kind of feedback it might receive from the world, like what does it mean when it gets certain kind of percepts. It also encodes the objectives of the agent, right? What is it trying to achieve? So this is kind of like when I say a planning model, you can kind of think of a representation of all of these kind of information. So probably most of you guys are like, generally when I'm talking about sequential decision making problem, the kind of techniques that most people are familiar with is usually reinforcement learning. To just kind of, so reinforcement learning and planning are kind of very closely related topics. So I just wanted to kind of at least tease them out a bit, at least in the canonical form. So you can kind of think of RL as going from experiences to some behavior, right? I'm well aware that not a lot, most of state-of-the-art RL doesn't really fit into that mold, but at least at a textbook level, you can kind of think of it as going from experience to some behavior. And planners or planning takes a model which encodes all the information and then generates a behavior, a plan or a policy or something. RL itself, like reinforcement learning itself, can use planners as a subcomponent in that it could take an experience, some kind of information that maybe some other information that some human specified or something, use some kind of model learning method to to develop a model of the world, and then it can use planners that have been developed, and then use that to generate the planning and policy. So these RL planning are not like completely separated topic. They can overlap. Even in planning, you can actually go from model to a behavior, and then use algorithms which are generally popular in RL area to come up with behaviors and so on. So they are very closely related topics. In this talk, I'll mostly be focusing on a simpler planning formalism, which is basically deterministic goal-directed planning problem. It's deterministic in the sense that the outcomes of the action are determined perfectly. As in, like, when the agent executes an action, it knows exactly what will happen, right? And it's goal-directed in the sense that the agent is trying to achieve or drive the task state to some goal states. So there might be a set of goal state which is desirable to the agent, and it's trying to drive the system to that state. And it's trying to do that by executing some actions it has. So actions are just things it can do in the world. And here, usually the solution of a deterministic goal-directed planning problem is usually a sequence of action, and what is usually called a plan. So it's just a sequence of action, and it doesn't have to observe the world or anything, because it knows what will happen after each action it executes. So if it knows the initial state, it can just come up with a sequence of action if one exists, execute it, and it can be kind of, if its model is accurate, it can be guaranteed that it would be in a goal state. There may be additional other optimization things, like it could try to optimize for the cost of the action. So it might want to come up with the least costly plan. And when I say optimal plan, I'm generally referring to the plan that has the minimal cost. And the other interesting thing is usually the automated planning community, the research community where a lot of research is happening in this area, are usually focused in developing what's called as a domain independent planner, which generally assume that planning problems or the model itself is encoded in some specified language, pre-specified language. So this language can be used to express all the information I was talking about, the dynamics of the world, the agent objectives, right? Any other constraints. And then this domain independent planner can take that model and will then just spit out a plan. So you don't have to worry about, right, creating like a specific planner for your problem. So there's going to be a domain independent planner. You just have to worry about specifying your model. So throughout the slides, you might see action descriptions of this kind. So this is just an example of such a model description, specifically a description of a single action. It's in a language called PDDL, which is very popular for deterministic goal-directed problems. And what this specific instance is saying is, it's kind of saying when the agent can do an action called picking up a block, which is specified in terms of these preconditions, which is kind of saying, okay, I can only pick up a block if my hand is empty, the agent's hand is empty, and the block is on the table, right? And the effects are basically saying what happens when you execute that action. And in this case, it's basically saying that when I execute pickup action, I'm holding the block, and my hand is no longer empty. There are some other effects like the block not on table. This is like a simplified thing I'm just showing you guys here. So so this is basically how these descriptions would look like. And you can there'll be some examples throughout, so you guys will know what I'm talking about when I present these descriptions. So just a small caveat, just because we are going to be focusing on deterministic goal-directed planning problem doesn't mean that any of the topics or the ideas we are going to talk about in this tutorial is going to be specifically limited to those settings. Okay? Everything we are going to be talking about is applicable in general to sequential decision-making problems. And in some cases, it's even applicable beyond it. Even for like single-shot problems like classification, some of these ideas are applicable. We are just going to focus on the simpler formalism because it gives us an easy way to specify and discuss the problems, right? And in fact, one of the open challenges still there is, how do we like coming up with formalizing and solving the ideas and problems we are going to talk about in this tutorial to more general settings. So that's something, if anybody's interested in following up on any of these topics, that might be something interesting to look at. So this is going to be our basic structure for the tutorial today. So I'm going to start with discussing this idea of what does it mean to be a human-aware planner. And that's where we want our systems to do. We are just going to also take a very quick look at some of the applications where these kind of systems could be useful. Then we will look at what I'll call as interpretable behavior. And we'll see some examples of interpretable behavior. I don't want to get into too much details right now. We'll go into more details when we reach there. And then we will talk about explanations, at least start the discussion on explanation by specifically looking at a type of explanation that we call model reconciliation. And the bulk of the discussion is going to on explanation will happen tomorrow. We'll also kind of talk about deceptive behavior. We won't go into as much details into deceptive behavior, but we'll also try to do it tomorrow. Okay. So let's start with what do I mean by human-aware planning problems. So this is kind of like a simplified representation of what traditional planning problem looks like. You have an agent. So this was what I was capturing by the original intelligent architecture diagram. So you have an agent, you have a model of the world, you have some goal that's specified in the model, and you are trying to come up with a sequence of action that lets you achieve that goal. Unfortunately, this is not the true complexity of the problems we are trying to solve. In most cases, these agents are not going to be isolated in the world. It's going to be operating along with, and in some cases cooperating with humans, right? And these humans have their own set of capabilities, their own set of intentions and things like that. So one of the things that people have tried to look at is, okay, we want to model, maybe this is specifically true in case of like collaborative settings and also in some cohabitation work, where the agent has to model what the human's capabilities are, what their goals are, and then try to reason about what plans they might follow. So there are some work along these lines. And we will use the notation MHR to kind of denote the robot's estimate of the human's action model. Okay, so this is one part. And you can start thinking about things like join plan, where some of the parts of the actions, some actions belongs to the agent and some actions belong to the human and so on. So there are some works that tries to take a look at these kind of things. Then you have the humans on the same side, you have the human's expectation of the robot. So people who are familiar with like psychology literature, you can kind of think about it as the human's theory of mind about the robot. So human has some expectation on the robot's capability, on what the robot's objectives are, and they are using these expectations to kind of come up with form beliefs of what the agent will try to do, right? How it will try to achieve and things like that. And this is where our the updated intelligent architecture thing comes in. So if the agent is to act successfully in the world, it needs to not only take into account its model of the world, which was in the original intelligent architecture diagram, but it also now needs to take into account what the human's model is and what the human thinks the robot's model is, because that's going to decide how the human would behave and what the human would expect from the robot and so on. So that's what this original picture was kind of pointing to. This was what the MHR and MRH, etc., was kind of representing. Okay, so in this particular tutorial, we won't get too much into modeling humans' capabilities as such. So we are not going to do a lot of collaborative things, but rather we are more going to be focused on reasoning about what the human expects from the robot. So this is the kind of thing that underlies a lot of explanations like interpretability problem when these expectations don't match. And so the thing that we will focus more on is this MRH, which is basically humans expect the belief about what the robot's model is. MR being the robot model, the subscript H here refers to the fact that it's a human's estimate of what the robot model is. And the central problem, as I was kind of pointing to earlier, that we will try to answer throughout this tutorial is going to be what happens when there are difference in what the human expects from the robot and what the robot would prefer to do. Or in some cases, what the robot can do, right? What could robot possibly do? And how do we address when there is this mismatch? One common reason why this mismatch could happen is because the robot's actual model might be different from what the human expects. And many of the techniques we will talk about today are going to kind of, today and tomorrow is going to kind of take into account like how we could explicitly try to reason about these kind of differences and how to incorporate them into your decision making. Okay, so first off, why should there be a difference, right? One of the reasons there could be a difference is because the user or the human we are interested in are not experts in AI systems, right? They could be everyday users. As such, their expectations on the capabilities could be very different from what the actual system is capable of and what the actual system's details are, right? So you might think agents are more capable, less capable, and things like that, right? Then you might have the case where the human might have a different expectation on what the state of the world is, right? The human may assume certain facts are true or might assume certain facts are false. And the robot might have a different picture because it has access to certain information the human doesn't, right? So even if they agree on the agent capabilities and stuff like that, they might just disagree on what the state of the current task is. Then the human could have different expectations on what the robot's objectives is, right? This is also this is very much possible even if the human was the one who specified the objectives. It might just be different because they weren't thinking correctly, right? You have all the Midas problems and stuff like that. Then there could be difference in sensor models, right? Like the parts of the world the human may see might be different from what the robot might see, as I was saying earlier. And there could also be a case where the human might have incorrect notions about what the robot's sensing capabilities are. And there is also the case that most of the time when we are talking about AI systems, and especially when we have like learned systems, there might be an inherent limitations or like inherent difficulty in how easy it is for the robot to reveal its model information to the human. Especially if you have like a parameterized model, something like a learned neural network that's encoding these, transition dynamics or reward function and stuff like that. It's not like if the robot wanted, it can't really just reveal that information easily to the human because in a sense, the human and the robot are thinking about the task in very different terms. And you have to kind of reconcile this before you can even try to reconcile the model differences. So the next question is, where do these mental model comes from, right? Like we've been talking about, okay, there is going to be a difference and we are going to account for this difference. And in some sense, that means we need to understand what the human's expectations about the robot is, right? What humans' theory of mind about the robot is. In some cases, these models are given directly, right? One example could be something like an urban search and rescue scenario. There is some kind of disaster and the robot is kind of deployed in the world to kind of get to do some operations, maybe like help people and stuff like that. In these cases, it might be possible for the robot to know what the human's mental model is because it could just be what the original map of the building was. because the robot is in the field, it might know that the building's map is no longer relevant and it has to change its model, but the human might not have that access to that information. So that's one case where you might have access to mental model. The other case is teaching, right? Especially in like structured classroom like teaching, if the agent is the teacher, it might have some idea about what the human knows, right? Like maybe based on some curricula or something like there might be some prerequisite knowledge, but like you can only take this course if you've taken these earlier courses. So it might have some idea about what the human knows. It's also possible to learn some kind of either the full model of the human, like there are some ways maybe like some interaction, it can try to learn what the human thinks of the robot, or it could also try to learn simpler model proxies that is enough for many of the problems. So one way is it might be given to us, and the other is basically we are going to learn it through interaction or some label data. So where are these? Why do we need these kind of human aware system, right? And where are these systems usually used at? So some simple things as you can kind of think about as I was saying, teaching, right? Intelligent tutoring systems. That's kind of obvious. We need some amount of mental modeling. There are already existing works that kind of try to talk about how do you model the student and how to give directed teaching with those kind of models and stuff like that. The other thing is basically human-robot interaction in general and social robotics specifically. So a lot of work in social robotics, like from people like Professor India Brazil, Professor Brian Scassaletti, and people like that who've looked at how to model the people that you'll be interacting with and how that model can drive the agent behavior and so on. So, but there could be a lot of other applications like personal assistance, decision support systems. You can imagine it's also quite relevant in a lot of teaming scenarios, right? Whether it's a factory floor or as I was talking about, urban search and rescue scenarios. So in generally, when we want the robot and human to act closely with one another, these kind of mental modeling could be extremely helpful. So for this particular tutorial, some things I'll be talking about is as an application basically, or as a motivating scenario we'll talk about is one thing was going to be human-robot interaction, particularly the urban search and rescue scenario, where you have a robot in the field and then you have a commander who's kind of monitoring the robot and trying to make sure it's doing the right thing. Then we'll have decision support system, which is basically there's a human expert who's trying to come up with some kind of plan of action or some kind of complicated sequence of activities. And the agent is basically acting as an assistant. They're trying to help the human make better decisions. And then there is this special applications, which is like a little more specific application, where basically you would be using some of these tools we will develop for the problem of acquiring models from the human. This is basically the specific one we look at is in the case of like goal-directed conversational agent. It's basically a person is trying to come up with a conversation script in a specific form, and the agent will try to help the human better author it. Like the difference here would be maybe the human did not specify it correctly, and then they have some model in their mind about how the conversation should go, and the system will use its mental modeling techniques to kind of help the process along. So these last two applications, I'll just kind of talk about it tomorrow. We won't go into it in too much detail today. When I'm using the examples, it'll be mostly from urban search and rescue scenarios. Okay, so before we get into any of the specific techniques, it's worth keeping in mind that adding these kind of mental modeling capabilities not only opens up a lot of opportunities for the robot to better team with, better help humans, it also opens up a lot of questions about the ethical nature of these things and other related questions. So one of the first things you have to keep in mind is if the robot, if it's an adversarial robot, for an effective adversarial agent, the skills it requires in many cases are similar. Because in many, for things like lying, one of the core capabilities you need is the ability to model the beliefs or the knowledge what the other person have, right? In a sense, lying requires these kind of mental modeling. This is say true also for other forms of deception, obfuscation, and things like that. In a sense, for to be an effective adversary, you kind of need to know your enemy, right? So we will kind of touch on some of these techniques tomorrow. And there are also additional ethical questions, right? Like the agent might not be an adversary. There might be cases where the agent could make white lies, right? Basically, it could give a false information if it knows that that false information could help uh, improve the team utility as a whole. So is it morally right to allow for these kind of behaviors? So this is again something we'll look at it. And also even beyond that, just the fact that you would have a system that's starting to model your beliefs and trying to adapt to your beliefs, you will also, at least most everyday users will start ascribing more capabilities to those kind of systems, and it might start ascribing emotions and things like that. So there is also a responsibility there to make sure that we are not inducing false trust in these systems, which could also cause further issues later on. Okay, so that's the first part of the tutorial, which is basically about human-aware planning. And hopefully you guys currently have a sense of what I mean when I say human-aware planning, which is basically taking into account the mental models of the user. The next thing we will talk about is what I'll call interpretable behavior. So going back to our human-aware planning setting, you have our agent. The agent has some model of the world, model of the task, right? And there's a human. So we'll, as I was saying, we won't consider a case where the human is actively participating in the world, as in like human is not executing actions in the world, but rather human is like, say, a supervisor. So they are looking at the agent's action and might make a call about, okay, this plan seems right, or this plan seems bad, and stuff like that. And it's human is more an observer, but it is in a supervisory role in some sense, right? So the part of the mental model we are most interested in is the human's expectation of the robot, which we were denoting by MRH. So the first set of techniques that we'll kind of look at is, as I was saying, is what I'm going to call interpretable behavior. And at a very high level, you can kind of think about these as behaviors that are specifically designed to induce some effect, some specific directed effect on the human's mental model without explicit communication. So I understand that's kind of vague. And the reason I'm kind of keeping it vague is because this term usually covers a lot of different details, like different kinds of behaviors. And we'll kind of go through three major categories right now. But in a general sense, the agent may choose to do these kind of things to maybe mold, in a sense, like to mold what the human's beliefs are. It could be beliefs about the robot's models, like robots' capabilities, robots' objectives, or it could be about beliefs about what the robot's future plans are, etc. It could also try to use these kind of interpretable behaviors to also avoid spooking the human, in a sense, right? By trying to avoid surprising the human, as we'll see. So speaking of which, the three, in a sense, interpretable behavior covers a lot of different works. And a lot of different works have been looked at very specific kinds of behavior and call them different things, like transparent behavior, or like what's like goal legible behavior, and so on and so forth. But in a general sense, you can take the entire space of the literature and kind of uh, uh, bucket them into three main categories. And these would be the three main categories we'll talk about today. And the first category is what's called as an explicable behavior. And this was the behavior I was talking about, where the basic goal here is for the agent to act in ways that are close to what the observer expects from the agent. Okay. Then you have legible behavior that is meant to communicate some information about the robot's model to the human observer. And then you have predictable behavior, which are behavior that are specifically selected so that if you see a part of the behavior, the human can easily predict what the rest of the behavior is going to be, right? So it's in some sense easy for the human to complete what the behavior, the total behavior is just from some prefix of it. So like if the human sees some, like start seeing the robot execute something or robot acting in the world, it can kind of figure out, okay, where it's going to go and so on. Okay, so we'll be looking at these three categories one by one. And as I was saying, first we'll start with explicable behavior. And what the explicable behavior is trying to address is a very simple problem, right? It's the problem when humans' expectation of the robot about its model, right? Which is basically MRH, does not match the robot's actual model MR. So one of the consequences of this fact is the thing that if the robot is purely using its model MR to come up with its behavior, let's say it's generating an optimal plan, right? And it decides to execute that. Because the human has a different model about the robot, it might think the robot is doing something dumb, in the sense that it might think the robot is doing an unsafe plan, an invalid plan, right? Or it might think the robot is doing a very extremely suboptimal plan, because they had very different notions about what the robot's capabilities are and things like that. And this could lead to, even in the best case, surprise on the human's end. In the worst case, there might be like safety problems, right? The human might try to intervene or might not allow the robot to execute and things like that. So the goal of explicable behavior here is to come up with behavior that in a sense conforms to human expectations. So here we won't use any kind of communication, but rather what it will do is the robot will try to, in a sense, choose behavior that will try to will more closely align with what the human expects. To kind of get a sense of what I'm talking about, let's go to the urban search and rescue scenario. There's a robot model, which is basically the map of the building. And then you have the human's belief about what that map is, right? So these black cells kind of represent obstacles that the robot can't go through. And the objective here is the robot to pick up this med kit. So like a first aid kit or something like that. Okay. So on the left, you can kind of see what the robot thinks the best plan of action is. On the right, you can kind of see what the human thinks the robot should do, right? Because it doesn't the human doesn't know that one of the cells which was previously blocked is no longer blocked, and the robot can just directly pass through it, right? So if the robot were to execute its optimal plan, it just goes up and then tries to go through what the human thinks is a blocked cell. The human commander, let's say the human is a commander who's observing the robot, could step in and say, no, stop the robot. It's trying to do something dangerous and things like that, right? So being explicable here would mean things like, one way of being explicable here would be, rather than doing what the human expects from the robot, it can do this more circuitous thing, right? It could try to, because what the human expects is still possible in the robot's model. It can just take the circuitous route and act in the way that the human would expect the robot to. Unfortunately, this is not always going to be the case. For like, this is an example where what the uh, uh, human expects from the robot is actually not feasible for the robot. So what's the best expected plan is not possible. But what the robot can kind of do is it can take this expected plan, or there might be a set of expected plan, and then see what is the closest plan it can do in its model. So the fact that we are talking about closeness, let's just for now assume that there is some kind of distance measure that we are given that captures what it means for for a plan to be close to another plan. So basically what this turns into, as far as the robot is concerned, is this multi-objective problem where it's trying to optimize for both its cost and also trying to come up with um, a plan that is as close to what the human's expected plan is, human's expected plan from the robot is, right? So it's trying to kind of balance these two factors and then trying to come up with the best plan it can. So generally, we don't directly do this kind of multi-objective thing. It's usually you turn it into like a single objective function, which is like a weighted sum of these two terms. And generally, you might even ignore the full cost function. It might just be, you might just use the distance as the dominant optimization criteria and just try to minimize that distance function. So I've been kind of vague about what that distance function is, because in the literature, there has been a lot of different kind of distance functions that have been looked at. So one possibility is, like a simple possibility is, think about the cost difference between expected plan and the robot's plan in the human's model. So the human might be forgiving if the robot does something that's not exactly what it is they are expecting to do, but seems more or less like close to optimal in terms of the cost, right? It's not doing something, in a sense, if you're thinking about cost as, in this case, the shortest distance, right? Even though as far as the human is concerned, the robot is not taking the shortest path, the path is close to being, in terms of the distance from the distance traversed by the robot, it's close to what would be the minimal distance. Then the human would think, okay, it is slightly inexplicable why it didn't take the shortest path, but the inexplicability is not that high. The distance function is not that high. There are other kinds of distance function that has been looked at, there are syntactic differences. You can think about, there are certain set of actions that the human expects the robot to do. And if those actions are not done, you would think, okay, they're further away from the expected plan than possible. And you could also look at some kind of learned distance function. In fact, the two specific things I'll just quickly cover. Both take into account, in some sense, a learned distance function. Okay, the first kind of work that we'll quickly look at is what I'll call as model-based explicable planning. So this is a case where the agent has access to both what the human's mental model is, right? This could be like the urban search and rescue scenario, where the human's original model about the robot is given, right? And we have, in some sense, there is a mechanism to compute what the expected plans is. It could be as simple as just running an optimal planner on the mental model and then figuring out what the expected plans is. And now the problem basically becomes, you have these information, and then you have the robot's model, right? And now the robot has to come up with a plan that is as close as possible with what the human expects, right? And one thing I did not quite talk about in the earlier quick intro about planning is a lot of planning successful planners makes use of heuristic search. So one easy way you can kind of guide this planning process is to kind of introduce some kind of heuristic that takes into account what the distance of the given plan is from the expected plan. So you can kind of come up with this new heuristic function and then kind of use it to come up with the plan. And this is a specific work. You can see the link at the bottom, which kind of uses this iterative planning process where you kind of threshold the explicability and then keep iterating and coming up with newer and newer plan. And as a heuristic function, it uses a learned distance function, where this distance function is learned from a set of test plans that were annotated by people. Where people would have taken these set of plans and said, okay, this plan seems far, this plan seems close. And then you try to learn a regression function that takes features about the plan to that distance function. And then you use it, you use that regression function to kind of come up with a heuristic function. Okay, so that was the model-based one. So you had the model, you had a way to come up with the expected plans, and then it was just kind of making use of those things in its planning process. Unfortunately, as I was saying, it might not always be possible to have access to these kind of models. So what would we do when we don't have those kind of models? So one thing that has been looked at in the literature is kind of having learning instead of actually learning the actual model, which can be an expensive process, because one of the things to keep in mind is this is not the human's model. So you can't just observe human acting in the world and try to infer what the model is. This is about humans' expectation of the robot, and it could be quite far from what the human's actual capabilities are. So they might have these very fantastical ideas about what the robot is capable of. So to learn this model, you need directly to interact with the human, and human has to give the information. So that can be a expensive process. So one thing you can do is, rather than learning the model directly, you can learn some kind of model proxy and then use that to kind of for whatever your purpose is. In this case, generating explicable plan. One of the things one of the works that has been looked at is kind of learning labeling models. The idea here being that when a person sees a plan, right? So if it makes sense to them, if it's being close to what they expect, they can kind of ascribe some kind of label to different parts of the plan. As in, like, if you think of plan as being a sequence of action, the humans say, okay, this first part of this action seems to be for doing this subtask. Or you can even have labels as simple as, okay, this action makes sense to me, this doesn't, right? It's kind of a simple labeling scheme. And if for a given action, we have, not a given action, for a given plan, there's a sequence of actions, we have these labels, right? One way to turn them into distance, or in a sense of an inexplicability score, is to look at how much of the part of the plan is unlabeled, right? If most of the plan is unlabeled, as in the person is saying, I can't make sense of most of these actions, you would say that is more inexplicable than a plan where more parts are labeled. So in general, we'll assume that there is a function that takes a set of labels over a plan and then gives you some kind of distance function. So obviously, we won't have a perfect labeling model, because it's going to be what the human have in their mind. But one good thing about it is you just need to learn a labeling function, right? In some sense, a classifier, which takes plans to a set of labels. In general, you can have some sequence-to-sequence models, which takes a plan and then creates a sequence of labels. And once you have such a labeling model, then you can now go back to the idea of taking a planner and then using this distance function as a heuristic, which in this case is basically just taking whatever the plan is, you have your learned model that takes the plan and generates a sequence of labels. Then you have a function that takes the generated sequence of labels and comes up with a distance, which then gets plugged into the planner as some kind of heuristic function. And then you're using that to kind of drive your planning process. Okay, I think we are getting close to the end of explicability. I won't, and I think we are also, I think that I took more time than I was originally expecting, so I won't spend too much time on this topic, but I just want to give you guys an idea that when it comes to explicable planning, the agent is kind of constrained by what they are capable of, right? What the agent is, the best thing the agent can do can still be quite far from what the human expects, right? Or what the human expects can be too costly for the robot to do. So one of these things you can do, especially if it's a structured environment where the human and the robot is meant to interact with each other over a long period of time, something you can do actually is to invest in designing the environment, or in some sense modifying an initial environment so that it is more it's more pliable to explicable plan generation. So I'll just motivate it with a simple example here. You have basically like a restaurant robot where the green arrows kind of shows what the human expects the robot to do, and the red arrows kind of show what the robot can do. The human expects the robot to like kind of squeeze its way through between these tables, but given the robot sensors and other safety concerns, it can't really do that. So it has to take the long way around. One way it can avoid the human from expecting these kind of things is would just be put some kind of barricade after the tables. So the robot is trying to make its way to the both G1 and G2, and by just placing some barriers here, what was originally very surprising for the human, where it was looking at this long way around route, by just putting these barriers, now it makes a lot more sense. I won't go into too much details, but the paper is given below, and there are some interesting trade-off that shows up in design for explicability that generally doesn't show up in the other, like just the behavior generation case. Okay, so before we go into the next section, I just wanted to take a minute to see if there were any questions. Yeah, so, okay, I don't see anything in the chat, but maybe we can take it at the end. Also, feel free to just maybe, if you have some pressing questions, or if I'm going too fast, feel free to like unmute yourself and ask me questions. Okay, so we've talked about what it means to be explicable. Where you basically have an agent that is trying to act in ways that are that basically aligns with what the human expects from the robot. Now, the next class of behavior that we look at is what's called as a legible behavior. And what we have here is, in some sense, an agent trying to communicate to the human some information about its model. Generally, that it could be any kind of information, but the thing that has been studied most and what we focus on is to communicate the agent's objective, which in this case, our assumption about the environment is basically its goal, right? The robot is trying to communicate what its goal is to the agent, the human, without explicit communication. So obviously, if it just says, okay, my goal is to do X, Y, Z, right? That's not going to be an interpretable behavior. The legible behavior, the point of legible behavior is it's trying to do so implicitly. So the first question is, why bother, right? Like when you have communication, why do it? It could be because the communication, explicit communication could just be too expensive, right? Maybe there is no way to communicate effectively to the human in a correct way, or the communication channel is not too noisy and so on and things like that. Also, implicit communication, like things like signaling and stuff like that, are part of, like, as an intrinsic part of human coordination. because it's just very efficient. You don't want to just stop and tell everything to the person you're working with, right? Like in many cases, implicit communication can be an extremely efficient tool, and that's something we'll see how we could do that in this case. So the basic idea here, as we are mostly going to focus on goal legibility, as in like communicating the goal of the robot, we'll have a case where the human has ascribed a set of possible goals. Okay, so you have the example urban search and rescue scenario here, right? And you have the two med kits. There's two possible med kits the robot might be trying to go towards. So the human knows it has to be one of these two med kits, but doesn't know which one it is. So the goal of the agent here is going to act in ways that makes it easier for the human to predict it as it's acting. So as soon as it starts doing its plan, the human can kind of figure out what it's trying to go towards, right? So in some sense, it's trying to synthesize behavior that kind of reduces the uncertainty the human has over these kind of the goals that the robot has. And as I was saying, it wants to resolve the uncertainty as early as possible. One way to do it in a simple case, like in a binary sense, would be, okay, the agent just picks a prefix that only allows for one of the goals. Okay, so let's assume in this urban search and rescue scenario, we'll add this kind of additional constraint that the robot can't visit any other cell it has visited previously. Okay, so now with this constraint, as soon as the robot goes towards the right, the human can more or less is kind of guaranteed that, okay, the robot is kind of going towards the medkit on the right, rather than the medkit on the left. But in most cases, even in this case, there is this possibility of like going the round way around and then trying to get to the medkit. So it's not always easy to have a case where you would have a small prefix which only allows for one goal, right? The other goal may be possible. So in a sense, we'll have to allow for some level of degrees of uncertainty. And the way we will kind of address it is we will take into account, kind of introduce this idea of doing a probabilistic goal legibility. Okay, so basically the idea would be, again, this, as I was saying, you have a set of goals, which is basically a set of models, and you are trying to select. So just to clarify, one of the assumptions being made here is you're assuming that the human is a Bayesian reasoner. So yeah, you can kind of think about it as the human sees some observation, which in this case is some behavior the robot is executing, and it's using the Bayesian base rule to kind of update the human's belief about what the agent's goal could be. And this is kind of, you can think of it as like a graphical model that kind of captures what the human's reasoning would be. So the goal here would be to come up with some kind of prefix that maximizes this term at the bottom. This is basically, you're trying to maximize the probability of the actual goal given the current prefix. So I actually won't go too much into details because we are kind of running out and there is so much left for day one. But the general idea is you have your priors over the model, you have this conditional probability of what is the likelihood of selecting a plan given this current goal, right? So in a sense, this probability is given by the computational model or the rationality assumptions that the human might ascribe to the robot. So if the human thinks the robot is an optimal agent, right? The pi m, like the probability of the plan pi given mg would be like a uniform distribution over all the optimal plans for that given the given goal. So you can be legible by selecting a plan that's only optimal for one of the goals and not optimal for the others. So it's kind of similar to what I was talking about, selecting a prefix that only allows for one completion. But generally, this is again, could be hard because humans aren't necessarily optimal reasoners, right? Even if the human thinks the robot is an optimal reasoner, they may not be capable of coming up with the right set of optimal plans. So the another model that's quite popular in the literature is what's called as a noisy rational model, which is basically you have this kind of a Gibbs distribution over plans, where the more costlier plan is given lower probabilities than the cheaper plans. And you also have this this beta parameter that's sometimes referred to as the coefficient of rationality. As it goes down, right, the difference between these probabilities becomes less. They kind of wash out. So with 0, all the plans get the same probability, and as it tends to infinity, you get more and more peaked distributions. So that's about with policy graphical, like policy goal legibility. And the idea here, the simple thing would be, now you get to this idea of, okay, this is a legible behavior because you are going, the plan you took towards that medkit, even though it's not optimal, right? In terms of for that goal, for the goal of medkit on the right, this plan is more closer to optimal than for a case if the goal where the robot has to go pick up the medkit on the left. So using our probabilistic model, like our Gibbs, like noisy rational model, if the human observes the robot going to right, it would start assigning more probability to the medkit on the right. Okay. So that was about legible behavior. And does anybody have any questions? Let me just quickly. Okay, so I think the chat is empty. Again, feel free to ask if you have any questions. Feel free to ask me, and we can also take it up like after the talk as well. Okay, the last group of interpretable behavior we are going to talk about is going to be predictable behavior. I won't spend too much time into it, but I think the idea should be more or less apparent from the name. The goal here is you're going to come up with plans that are easy for the robot, the human to kind of predict. So a lot of this work goes back into work done in HRI. Both legibility and predictability was kind of introduced in HRI. HRI being human-robot interaction. So it's a field that specifically focuses on generating robot behavior that are in some sense are better suited, or coming up with interaction mechanisms for robot and humans. So the simplest form of predictable behavior is you're just going to come up with, just going back to our probabilistic model, you're just going to come up with a behavior that the human thinks is more likely, right? So you're going to, in a sense, here, you're going to select a plan that the human would ascribe more probability to. And if it's just, the human is just thinking it's an optimal agent who takes the shortest route, this would more or less means just selecting the plan which has the lowest cost, right? So you're just going to, as we were talking about, it's the noisy rational model and stuff like that. The human would assign more probability to the one with the lower cost. So that would be the more predictable one. So this is not as interesting. A more interesting version of this is what's called as a T-predictable planning, which is basically the same idea, which is that you're trying to come up with plans which have higher likelihood. But the interesting thing is you are trying to set it up in such a way that you only need to guarantee high predictability after first T steps. That's where the T kind of comes from. after the first T actions, the human should have a high predictability score. So actually in the formula, it should have said capital T and T plus, or more likely the description should say first small T actions. So basically the idea being after the first T actions, the rest of the plan seems has very high probability. And why that's a more interesting setting than the other is because this allows for the robot to initially do very unlikely actions, right? So one way of thinking about it is if there is first T steps and there are multiple possible paths the robot could do, the robot, if it's possible, the robot could have taken the first T steps to kind of block some of the paths, right? Once the other paths are blocked, the rest of the path, rest of the plan is very easy to predict because there's only one path left, right? So the T predictability kind of allows for those kind of behaviors to do. So in this specific example, it's not as like not as like extra like exciting as the example I was giving, but why it is T predictable is the first two steps where it's doing a suboptimal thing. So it's going towards right when so in general predictability, specifically for cases where the human knows what the robot's objectives are. So there's only a single goal and stuff like that. So there is no uncertainty over goals and models and things of that nature. So there is one objective here, get to the medkit, and then the first two steps of the robot, the actual path itself is extremely suboptimal for that policy because it's going that way when it should have just gone to the left and just picked up the plug. But once it takes those two steps, the rest of the plan, when you condition it on those first two steps, the rest of the plan is very easy to predict because it's like more or less you've tunneled the agent into this specific path and it can just follow it. So that makes it more predictable. So that's why I think T predictability is an interesting variant on the usual predictability thing. And again, you can kind of look at the paper itself to get more details on it. Okay. That wraps up our discussion on interpretable behaviors. And for the rest of the talk, I just, for the day one, I just more or less wanted to talk about explanations and kind of get started on this topic called model reconciliation. But before we do that, do we have any questions? Does anybody have any questions about anything we covered here? Whether that's about planning, whether it's about any of the interpretable behaviors, some specific techniques, or even the motivation, right? Like, why are we doing this? You guys don't believe in mental models and stuff like that. So
yes,
feel free to let, yeah.
There is one question.
Well, I've got a question that concerns maybe both three kinds of interpretable behaviors. So explicable, legible, and predictable all go through the human user, but it tends to restrict the.
I couldn't quite hear you. Could you repeat that?
And I wonder to what extent that
we do not understand.
Harmful because even we're in an environment that can evolve, that can change, if it has no degree of freedom, it cannot adapt during the execution of the plan.
I'm sorry, I couldn't just.
I also hear nothing. I mean, it's not loud enough.
Maybe you can put it in the chat and then it might be easier for me to follow if it's possible. Hello? Okay. Okay. Is the person still there? Maybe we can get back to that question at the end. Maybe just feel free to put it in the chat and I can just follow. I can just answer it as soon as I see it in the chat. Okay. Let me just jump back to explanation things. And we can talk about it. Okay. So you guys can still hear me, right? At least there are no issues there.
Yeah,
hopefully. Okay, cool. Okay, going back to the HumanAware Planning setting. So again, I won't bore you guys again with all of these details, but just want to reiterate our explicability planning problem, right? So this was the case where there was a human who has some expectations from the robot. Then you have a robot who has their own model, their own algorithms and their own inferential capabilities and stuff like that. And they are coming up with a plan or policy based on those models. And what the human expects from the robot may not match what the robot thinks is the best thing to do. And one of the solutions strategies, when there's such a mismatch, right, it could lead to confusion and so on and so forth. One of the strategies we talked about earlier was, okay, let's not worry as much about being optimal, right? Let's not worry about robot doing what it thinks is the best thing to do. Let's try to be as close to what the human expects is the right thing to do. Okay, so that's one thing, one possible solution. The other thing that the robot could have done is it can just stick to what it thinks is the right thing to do, which is its optimal plan in some cases. It might be some other valid plan or whatever, depending on its algorithms. And rather, it could try to explain its decisions, right? In some sense, it can try to justify why it did this as opposed to what the human was expecting from the robot. And this is the part that we focus on. And when I talk about explanation through this talk and through tomorrow's talk, I'm generally talking about why questions, right? In general, this is usually sometimes called as contrastive queries, but the usually explanations, I will treat it as an answer to the question, why was this plan by star MR, which was what the robot did, was selected? Or it might be an explicit contrastive question in the sense of, why was this plan selected over this other set of plans I was expecting, right? Or this other plan I was expecting. And that's the what I'll treat it as explanations. And in general, what we will see with explanations is, in a sense, explanations is about reconciling the differences in expectations. And that, in a sense, would either mean reconciling the knowledge differences, this is basically the model, right? What the human might think, there might be a different model from what the robot has. And in some other cases, it could be about reconciling inferential differences. The human just might not be as capable of a reasoner as the robot. Might think some invalid plan is correct, or might overlook some plans and stuff like that. And one of the other challenges you might have to also address is the fact that the robot's model, right, is represented in terms that the human cannot make sense of. So there might also be this difference in vocabulary. I'll just use the term vocabulary to kind of loosely talk about the representation scheme for the model. So for explanation, you might also have to, as part of explanation, you might also have to reconcile these kind of model, the vocabulary differences. So these would be these three dimensions. You can kind of think about these three dimensions of explanations. I'll use them as a framework to kind of talk about different kinds of works, at least some of the works that we'll be talking about in this tutorial and tomorrow. Okay, and we'll talk about how it helps achieve reconciling knowledge differences, how it helps reconciling inferential differences, differences in inferential capabilities, how it helps reconcile vocabulary differences, and so on. Okay, the first one is the most obvious one, which is basically what happens when there is a difference in models. And for now, we'll assume, okay, the models are represented in symmetric vocabulary. So they are represented in, the human's model is basically already represented in a scheme that can be understood by the human, right? So usually I don't know if you guys remember, there was this kind of description languages, right? One of the good things about description languages is it's meant to be written and read by people. So if you already have this kind of a representation from the robot, which is written in terms, as in like, there are things like state fluents, right? They are usually state features. You can kind of think about as state variables or state features. They are already in terms that the human makes sense of. You can technically kind of show the kind of reveal this model to the human. So one obvious way to kind of reconcile any of these differences would be, okay, the robot takes its entire model and kind of dumps it on the human. Okay, so this is usually called as model patch explanation, and they're generally not a good idea because the human, the robot model could be huge and could be different with the human in so many different ways. And many of them might have nothing to do with the plan or the question at hand, right? So dumping this entire model to the human would just result in the human being confused and not having a sense of what exactly the robot is trying to convey. So what instead the specific method we'll talk about is, we'll talk about this idea of giving the minimal amount of model differences. Okay, just to step back, this entire idea of explanations as explanations being performed as like explanations in some sense helping reduce the differences between the human's expected model and the robot's model. We'll refer to them, or at least it's referred to in the literature as model reconciliation explanation. So all these explanations are in a sense reconciling the human's expected model with the robot's model, right? So even the case earlier where the robot is dumping its entire model to the human is in a sense some kind of model reconciliation explanation, just extremely inefficient. The specific thing we will talk about is what's called as a minimally complete explanation. It is in the sense that you're going to try to find out the minimal amount of information that the robot needs to give to the human so that it makes sense of the plan at hand. So I think I'll just give a quick overview of what this example specifically is. So this is something that happened at our lab where we had a fetch robot, which basically someone was operating, and it just fell on its head and broke its head in a sense, right? So why did it happen? And this was a classic example of model mismatch. So what the operator did not know was that you can think about the move action. There's a move action, and the move action has these preconditions, which is basically certain things that has to be satisfied for the action to be executed safely, was that the robot can only move when its hand is tucked and when it's crouched. Okay. As far as the human is concerned, okay, it doesn't have to be the case. It doesn't have the hand doesn't have to be tucked. It doesn't have to be crouched. It can just move right from one point to another. And this basic mismatch could lead, as shown in the picture, could lead to disaster, right? But in a scenario, if the robot were to say, okay, the plan about moving one object from one location to another involves picking up that object, tucking its hand, then moving from location 1 to location 2, and then putting it down. Okay, this operator who did not know about the fact that there is a hand tuck precondition might object and say, oh, okay, that's like seems dumb. You're doing unnecessary work. Just remove the tuck action and just execute this smaller plan. And as we've seen, this could lead to a problem. So here the explanation would, in some sense, would say the human knows that the tuck action has this effect called hand will get tucked. So one thing you can do is it just have to say, okay, I have this precondition for move called hand tuck. So now with this new information, you can kind of see this plan requires the tuck action, right? So generally, how do we operationalize it? One way to think about it is you can think about it as a search over the space of models. You have your humans expected model at one end, and then you have the robots actual model on the other end. And the search space consists of what are the changes I can make, right, on the humans model so that it gets closer and closer to the robot model as possible, right? And I want to make as minimal a number of changes as possible so that the plan at hand will make sense. I won't go into too much details as because we are kind of running out of time. But the idea would be you're going to make minimal number of changes till some condition is met. Usually in MC, the original work, that condition was we will stop the search as soon as we reach a model where the plan is optimal, right? So in a sense, if plan is optimal, and the human can say, understand that it's optimal, then it's all good, right? The human won't ask any more questions because this is the best it can do, right? But it doesn't always have to be optimality, because optimality can be an expensive process, and usually people not always care about optimality, right? You can test for weaker things like validity. You can say, okay, I'm going to make enough changes so that the plan is valid. Or instead of full test for optimality, you can have some necessary conditions for optimality. Like you could search for make enough changes that every step in the plan is contributing something, right? In that case, tuck action was contributing to the fact that hand tucked is a precondition for the action move and so on. And you can also have a contrastive version where you only give enough information so that it looks better than what the human was expecting. This is especially helpful if the person had upfront told the robot, why did you tuck your hand? And instead you could have done this other plan where tucking hand is not required. So you only have to make enough changes so that it looks better than what was the human expecting. So for now, I'm going to stop here and we'll pick back up on for day 2. Let me just check. I think there's some questions in the chat. Let me check the questions and you can also ask me more questions. Yeah. Okay. So this is an extremely, I have 2 questions and both of them are really, really good questions. Okay. So I'll just go from bottom to top. So the interesting part, okay, I'll just repeat the question. Question was, to what extent do all these ways of taking account of mental models augment computational? In some sense, I'm understanding it as how does it take into account the computational difficulty of related tasks? So there is 2 ways of, at least from my end, there's 2 ways of making sense of that question. Is are these like the problem of generating explicable behavior, is it computationally feasible, or is it like a costly process? Or you can also ask a related question of how does the computational complexity of the task affect the human's expectations of it? Right. So both are interesting questions. So to kind of, these are, so in general, the first question, how computationally expensive this is in general, planning is a complex reasoning problem. So if you are into all these complexity results, plan existence is p-space complete problem. So, but the good thing is there are a lot of efficient solvers out there. And if you're specifically looking into these kind of explicable planning and stuff like that, once you have a heuristic function, you could technically plug it into all these things and it'll help you generate these kind of plans. They are slightly harder than planning problem because you're using these handcrafted heuristics, and might not be as easy to solve as the original planning problem, but they are still, you're using like well-engineered solutions and stuff like that. The other part that's a little more interesting is what happens when the problem itself is hard, and how does it reflect human expectation? So the general idea is to kind of think about it is humans aren't the best reasoners out there, right? They are generally, the way you would model humans in most cases is as, in some sense, bounded rational agents. They're not rational agents, but bounded rational in the sense that if you have like complex enough problems, it's kind of unlikely the human would be able to come up with the best solutions and stuff like that. And there are some ways you can incorporate that into your solution process. One was what I was talking about, the noisy rational model. So the beta parameter, in a sense, can capture that. So by putting low enough beta values, you are reflecting the fact that the humans, in some sense, you're reflecting the fact that humans' reasoning capabilities are limited. The other interesting thing is if you're learning things like distance function. So in this case, you are learning a labeling function, right? If you're learning it, since it's learned from the human's data, it also reflects in some sense the human's capabilities about reasoning. So you might actually see that explicable planning might require doing things like doing behavior that are simpler or easier to understand, and that gets automatically folded into the learning process because you're collecting data from the human. Okay, the next question was, to what extent can this predictability of human behavior be harmful to the capacity of the system to adapt to new situations? Okay, let me think. It's not quite about adapting to the new situation, is because you will have to define what new situation is, right? Like if it's just a different task, the whole process starts anew, right? You have new questions of predictability and things like that. But there is this interesting problem that if the new situation is just about the robots model is getting updated, right? Something happened, like in the urban search and rescue scenario, something happened and the map has changed. And because you're trying to be predictable, you're trying to be explicable, or you're trying to be legible, you are acting in ways that are what the human would expect. And you're in some sense maybe giving up on new opportunities that you could have otherwise utilized, right? Maybe there's like, for some reason, some wall broke down and now there's like a shortcut, right? And instead of taking the shortcut, you're taking the longer route because that's what a human expects. So in a sense, yes, you are giving out, specifically for the behavioral part, where it's no explicit communication, it's just implicit communication on just interpretable behavior. You could, in some case, be giving up opportunities. And one way to address it is by using communication. If there is communication available, you can use communications to like capabilities to kind of overcome this, right? If the model changed and informing that update to the human will make the process a lot easier for the robot, it should do that, right? It should say, okay, oh no, now this shortcut has appeared, and this makes it a lot easier. And something we will see tomorrow is we will see how we can combine explanations, that is communication part, with behavior generation, which is explicability part. So you will give only as much information as is required, and the rest of the way you will try to align with what the human expects. So that way you can kind of trade off. Okay, so hopefully that made sense. Are there any other questions? I think maybe I'm over time a little bit, but yeah. Let me know if there are any other questions, and otherwise.